Okay guys, one more slideshow, one more video for today. Characteristic interactions. We just spoke about Bremsstrahlung interactions. Characteristic interactions are a little bit different. They emit the same kind of X-ray. They're produced in similar ways, but X-ray energy produced by characteristic interactions is a little bit more predictable. And as it says here on one of these slides, it's actually more useful for diagnostic imaging. So we're going to see a lot of that in our future. First of all, what is characteristic X-ray? Is first of all, it's created from heavy elements that make the electrons make transitions within atomic energy levels. You got a picture of an atom in just a minute. We'll take a look at. Maybe that'll make a little bit more sense to you. But before we go to that, I want to point out one other thing too. You may have heard the term K-shell energy or K-shell interactions, K-shell radiation. You seem to be hearing that more these days than in the past. It really is the same as characteristic. I've always called it characteristic interactions or characteristic X-ray or radiation, but it may be called, as it says here, K-shell. And when we describe how it's actually created, you'll understand where this term K-shell energy comes from. So let's move on to that. This is a picture of an atom again. We'll see the nucleus here, and it's surrounded by several different shells or several different layers of electrons. Just like with the Bremsstrahlung radiation earlier, what we're going to do is shoot an incident electron, again coming from the cathode element of our X-ray tube. We're going to shoot it into a tungsten or some whatever metal we've made our target out of. This is the target atom inside our anode in our X-ray tube, and it's going to interact with some of these subatomic particles. But unlike the Bremsstrahlung radiation, where the incident electron just came in close proximity to the nucleus of this atom, what's going to happen in this situation is it's actually going to come in here and impinge on or interact with an inner shell electron in the K shell, and what it's going to do is it's going to thump that electron out of there. It's going to thump it out of orbit. As a matter of fact, all the way out of the atom. Excuse me. And that's all well and good, but here's the thing about electrons and about atoms and about the energy inside of there. This nucleus has a positive charge on it. It expects to have a full K-shell here. K-shell is the innermost shell of electrons in an atom, and to be full, that shell has to have 2 electrons in it. Now, if it's a hydrogen atom, it only has 1 electron in there because there's only 1 proton in a hydrogen nucleus. So in that case, it doesn't have 2. But any other atom would have a minimum, would have 2 electrons in here. Anyway, the binding force between this nucleus and this K shell is very, very strong relative to the other shells of electrons. So it's going to demand, this nucleus is going to demand 2 electrons in this K shell. So if one of them gets thumped out, it's got to fill that up. Where's it going to get that from? Well, it's going to get it from this next shell out here called the L shell. This electron will fill the hole created when this electron left out. So now the atom is relatively happy or happier than it was before because its inner shell is full of electrons. When this electron moved from this L shell to the K shell, it released energy. And you guessed it, that energy was released in the form of X-ray energy coming out of this angle here. And we can see it has a relatively high frequency with it. And just like with the Bremsstrahlung, what that indicates is this high frequency is also associated with a relatively high energy level. So we get a lot of radiation, X-ray radiation, produced when this L shell fills that K shell electron. But what happens is we leave a hole here in the L shell. We expect to see 8 electrons in that shell, and that's what the nucleus demands. So what it's going to do is going to pull an electron from this shell to fill that hole. And when it does that, it's going to produce radiation coming off a little bit different angle, a little bit lower frequency, and as a result, lower energy associated with that transition. But it is X-ray energy. We see about 59 keV of energy produced from a K-shell transition, and about 8 9, I can't see, keV associated with the transition of the L shell. When that happens, guess what? We left a hole in this shell. So that's going to be filled by outer shell, which is going to leave a hole here, which is going to be filled by this shell, and so on and so forth. And each time one of these inner shells loses an electron, it's going to be filled by an outer shell electron. And when that transition takes place, it's going to result in lower and lower amounts of X-ray energy being produced. So much lower, as a matter of fact, that we really don't pay much attention to these out here. Even though it is X-ray energy, it's so weak. It's really, it doesn't amount to anything. But these two here will result in usable X-ray energy for us. This K-shell transition is where we get most of that, and that's why they call this K-shell interactions. Characteristic or K-shell means the same thing. Okay. Just a table showing the relative energy coming out of those. K-shell will get about 70 kiloelectron volts. L shell transition will get about 12, and then for an M shell 3, for an N shell a half, and then almost nothing for 0. So again, as we go further and further out, these transitions have less effect on us. This is what's happening inside that X-ray tube. Think about your X-ray tube again. Remember the filament over here, our cathode, called cathode because it's negative charge on it. The anode is going to be more positive than the cathode, so anode is a positive term. This is our target that we talked about inside the tube. We're going to boil these electrons off of this filament. They're going to be attracted in high speed to this direction here, and they're going to interact with the atoms. Each one of these little donut shapes is considered to be an atom in this anode. And we see two different kinds of interactions taking place. You'll notice on this number 2 here, where it interacts with this atom, it actually just changes direction. That is a Bremsstrahlung or a braking interaction. But that same electron that came through here and interacted with this atom in this target in a Bremsstrahlung or braking fashion can come on up here then and interact. This loop indicates a characteristic or K-shell interaction with another atom in the same target. So we can have two interactions, two of the same type or two different types of interactions from the same incident electron coming in here. So we see different examples of electrons, 6 different examples interacting here. It is possible, because we said earlier that there's a lot of empty space in atoms. It's very possible that an incident electron could come shooting through this target and miss every atom in there and not interact with it at all. That happens. So what we do is we shoot so many electrons in here that we're bound to have some interactions, and those interactions are somewhat unpredictable, but all of them result in some kind of X-ray energy that comes off of our target here. I'll let you read this slide for yourself. One more slide to look at. Two terms that we need to be extremely familiar with, and we mentioned them earlier, but you're going to see them a lot over the next few weeks, is quantity and quality of X-rays. They mean similar things but different, and we're going to find out when we talk about something called the prime factors that these things are always something that we take into consideration, and so do the X-ray technologists who actually run the machines. So let's talk about them a minute. Quality of X-rays. You know, quality is a good, bad thing. It's better or it's worse. It's something to do with quality. So radiation quality, or the penetrating power of an X-ray beam, is determined by the KVP. And it also says employed filtration. We haven't talked about filtration yet, but we will. So the main thing to take away from this is the quality, how good the X-ray is based on how much we turn up the KVP, or the kiloelectron volts, that's or kilovoltage, excuse me, applied to that X-ray tube. And it really says what we're really saying is the higher we crank the KVP, the further our X-ray energy will penetrate. So that's quality. Quantity, as you probably already guessed, has to do with a numeric value of some kind. The amount of X-rays influenced by many factors. It is the area under a curve of X-ray emission spectrum, which we'll see that later. But basically what it means is how much X-ray energy we're actually producing. And there's a number of ways we can affect that. First of all, as we said earlier, the more electrons we boil off of our filament, the more target or more interacting, more incident electrons, I should say, are interacting with the target, which creates more radiation. Also, if we crank up the KVP, there's more chance for high-speed interactions, and if we increase the thickness of our target, that will give more atoms, the electrons, more opportunity to interact with some atoms in there. So all of those things can affect the quantity of X-rays. And again, we'll talk about this more as we go along, but just keep these two terms in mind and get them clear in your head, because it's going to help us a whole lot going forward. Okay, that's it for today, guys.